and you can see how incredible it's now, like the speed leveraging the Mac GPU. Hi, welcome to this new video. I'm Sergio, I'm a computer vision consultant, developer and course instructor. I build computer vision solutions to help companies improve their process efficiency, reliability and scalability. Today we're going to see the installation of object detection on the Mac M1. We will see how to write the code from scratch in Python to detect objects on a video. And then we will see also how to leverage the graphic card from the M1 device to get a very high performance for the detection. So the reason why I'm doing this is first to show you how to install and use object detection on the Mac M1, but also how to make this much faster and see how fast the Mac M1 can work with object detection. In addition, at the end of this video, I'm going also to do some benchmarks. So I'm going to compare the Mac M1 with the GPU, with the CPU, also with the a Windows computer with an Nvidia RTX 3060, and also maybe another graphic card like the GTX 1660 Ti. So let's go. Let's start first from the installation of the libraries that we need for object detection. So we need to open the terminal. So we have terminal and then pip install Ultralytics, and then we press enter. I don't go with this because I have this already installed, but that's the only installation that you have to do for Python to have all the libraries that we need for object detection. Because Ultralytics is going to install a lot of other dependencies, like for example, Opencv, which is the library that we use for image processing in general. Then I created a project in PyCharm. I will not go into details about PyCharm. You can use any editor that you prefer to write your Python code. Just follow along with everything that I'm writing. I'm going to use this file right here. We will play with this, which is docs.mp4, which is the video file where we're going to detect dogs, and of course you can use your own file to detect your own objects. And all the codes that I'm writing right here will be available to download in the link that I will put down below in the description, so that you can also get access to the same file, docs.mp4, and the code. But of course, for this exercise, I recommend to not download the code, but write the code, follow the video and just writing by yourself without just using the code that like ready, without writing it yourself. So let's now go with loading first the video with the Opencv library. So we start writing the code, import CV2, which is the Opencv library and was installed together with Ultralytics. Let's now load the video. To load the video, we need to create a capture object, cap equals cv2.video capture, and then we need to put the path of the video. So I have the video in the same folder, so the path is just docs.mp4. If you have the video on another folder, you need to put the full path of the video. So docs.mp4, and let's now go with taking the frames from this video. So ret frame equals cap.read. Now this function is going to return ret. It's just say if there is a frame, it says true, otherwise it's false, and then the frame that we want to use. Now let's show the frame on the screen. cv2.im show. Let's call the window EMG, and then what do we want to display? We want to display frame. Now when we run this code, so let's run this one very quickly. So the code gets executed. It opens a window with the frame, and then it closes because the execution of the Python code finishes and then everything stops. So we need a awaitkey event, cv2.wait to keep everything open on hold until we press a key. So we run this one, and now we see that everything is working, but we have only one image, and that's all. So we press a key and it closes. That's because we need to, first let me close this one. We have a capture object, but we are taking only one frame. Consider it's a video is nothing more than a frame after the other. we need to get all the frames in a loop. So what we will do is we put everything in a while loop, while true, and then everything inside. So now it takes the frame, it shows the frame, it's waiting for us to press a key, and then it starts again, taking the next frame and so on. So as you see right now, it's loading the frame, it's waiting to press a key, I press a key, it takes another frame, and so on. So I don't want this to wait for me to press a key. Instead, we want this to go in real time. So instead of CV2 wait key 0, we put CV2.wait key 1. So the frame it's not on hold anymore, but it's just waiting 1 millisecond and then going to the next frame. Key. So let's run this again, and you see, of course, it's very, very fast. But I can't do anything. I cannot close it. If I press a key, nothing is working. What do we need to stop it? We need a key event. So when you press a key, this key corresponds to some value. If the key is equal to 27, which is the S key on the keyboard, we want to break the loop, so it stops the video. This will be enough, but there is another thing that I want to show you. We have an error right now. What is happening? It's taking frame after frame. That at some point there are no more frames. So when there are no more frames, frame is empty, there is nothing, it's none. We try to show a frame that doesn't exist. So on line 8 we're getting an error, and it's clearly explained. Size is not greater than 0. So there is no frame, and we're trying to show a frame that doesn't exist. In order to avoid this, we need to say if there are no more frames. So if not red, it means there are no more frames. We want to break the loop. So we can stop the loop, we can break for two reasons. Either there are no more frames, or we want to quit, so we press a key, the 27, which is the S key on the keyboard, and it quits. So if I run this right now, I press the S key, it stops. So let's now do one thing. Another thing is cap.release. It usually doesn't happen like for such short codes, but when this is into a bigger program, this is essential, cap.release. Because if you are using a video and then you are not using the video anymore, still the capture object is holding the video. So in case you take the video from other programs, it say like you cannot access the night because Python is holding the video until the code is executing. So cap.release to release the video, and then cv2.destroy all windows to close any window that might be open from Opencv. So far, just very basic computer vision to load an image and a video. Let's now go further, because the goal of this video is object detection. So now we can use the object detection code. We're going to use Ultralytics. From Ultralytics, import YOLO. We use Ultralytics because at the moment I'm recording this video, it's like the fastest and latest deep learning object detection model with the YOLO version 8. It's very fast, very precise, very accurate, and it can leverage, it's using PyTorch, so it can leverage the graphic card of the Mac M1, which is great. So from Ultralytics we import YOLO. Now we need to load the object detection model. So we're going to say model equals YOLO, and then here we can put the path of the object detection model. If we put just YOLO v8m.pt, it's going to automatically download this. So we have 5 different models, the YOLO version 8m, which is the medium. Then we have smaller versions, bigger version. The smaller is less precise but faster, the bigger is more precise but slower. We'll not get into details of this. Let's stick with the default version, YOLO v8m. And what can we do with this YOLO version? This is a YOLO pre-trained model that can detect 80 different classes. 80 different classes. Which one? We will see later what we can detect. Let's now write the code to detect the objects. Once we have the model loaded, to detect the objects, we need to pass the frame inside the model, and the model will tell, okay, in this image there is bounding boxes, so the position of the object, this is the object, this is the confidence of the detection. So results equals model. Inside the model we pass the frame. I'm going now to put CV2 await key 0 to keep everything on hold so that I can print something and it doesn't keep printing everything in the loop. So results, let's now slowly understand what's happening with results. So let's print results and let's run the code. It takes a while to run object detection, so it's not as fast as when we run just basic Opencv. First, now it's downloading the model because we don't have the model. So the model is a PyTorch file with the size of around 50 megabytes, at least this default medium model. Then once it has the model, it needs to load the model on the memory. So that's why it takes a while to start. Let's now see our output. Our output is a big array with a lot of information inside. And this information regarding the position of the object, the class of the object, and so on. Now we need to extract this information. So we are now going to do that. In order to extract this information, we take from results, we take a single result equals, so results, and then 0. And let's now print result and run this again. Why am I doing this? Because the code is made in a way that you can pass an array with multiple images at the same time. Considering we are using only one image at a time, we are taking like the first index, so that's why I put result. And now from result we can access the bounding boxes. So let's say bounding boxes equals result dot bbox boxes dot xyxy. Should be like this. Let's now print this one. Print boxes, and let's now run this one. So this is to get like the point. Okay, that's what we get. With this we're getting bounding boxes. We have like 2 points, top left, so this point top left, and right bottom, which we can use, so x1 and x2, x1, y1, x2, y2, that we can use to draw the bounding boxes. And so we have this. Now, of course, we need to optimize this. The information is not ready for us to draw it and to put it on the screen because we have 671 point something, 267 point something, and this is a tensor from PyTorch, and we can't use this information right away inside Opencv. So we need some more pre-processing. So what we should do is to say to CPU, and then we're going to convert everything into a numpy array, np.array. So I'm going to import numpy as np, numpy array, and then data type equals int. Because we want an integer, we don't want float numbers when we're drawing a pixel. If we have like 667 point something, either it's 667, either 668. We don't want float numbers on integers. So let's now print again bounding boxes, print b boxes, and then let's run this again. So now the way I'm extracting this code in a way, it requires a lot of pre-processing, which normally can be simplified. So we can do a class, or we can do like some function and classes that do everything for us for this to have a very clean code later. And that's what I do when I build some project. I usually have classes and everything well organized. The only reason why I'm doing this right now is so that you can play around with this from scratch, and it's a good exercise for you to understand how we extract the information from the original library and so on. So now you see we have bounding boxes, and we have 661, 71, 267, and so on. So we have numpy array, we have only integers, and that's exactly what we wanted. And from this, we can now extract what we need. So consider we have multiple bounding boxes, we want just a bounding box so that we can display the detection. For B box in bounding boxes, let's extract X, Y, X2, Y2 equals B box. So if we print now X, let's just print a couple of them, X and Y, then Y like this. I just want to make sure that we are extracting everything correctly. Like this. So we have X and Y, you see everything is extracted correctly. So what do we do? Once we have X and Y, X2, Y2, we can draw a rectangle, because this is the position of each single object that it's detected on the screen. So we do cv2.rectangle. Where do we want to draw the rectangle? We want to draw the rectangle on the frame. Then to draw a rectangle, we need 2 points. We need X and Y, which is the top left point, and X2, Y2, which is the right bottom point. Then we need to decide what color do we want to make this rectangle. Let's make this rectangle red, because it's easier to see. It's the best color for this contrast that we have in this video. So to make a color, we need 3 values, BGR format. So let's say 0 of blue, 0 of green from 0 to 255, and let's put around 225 of red. And then how thick do we want the rectangle? Let's say 2 pixels, so it's well visible. And let's now run this one. So let's stop this and let's now run this. And we have now, as you see, the dogs. We can do this also more in real time. Now I put cv2 awaitkey 0, so everything is on hold. Now we have object detection already working, and this is a first step. We can of course add more information. We can add what is the class of these objects. We can add the confidence score. So let's do that. Let's maybe add at least the class. So classes equals np.array. We use the same, so it's a result dot boxes dot class. It should be class, but I'm going to double check to make sure. So from the documentation, CLS, so not class, CLS dot CPU, and then we use same data type int. So what do we do now? We do for class, let's say better object class, obj, let's say CLS for class in zip. So we're not going to extract 2 arrays at the same time, bounding boxes and classes. And let's now show this on the screen. So classes and boxes are 2 identical sizes array. So for the first bounding box or the first object, we also have like the class. So what this bounding box is. And so for the second, so they are consequential. So classes CLS cv2.put text. Where do we want to put the text? On the frame. And what's the text? We want to display the class, so we display a string of CLS. Now where do we want to place the text? Let's place the text on X and Y on the top left, but I don't want the text to overlap the box, so I'm going to put it a bit above, so let's say -5, and I'm going to draw the text after the rectangle. cv2.put text on the frame, string of class, the position x, y -5, and then we need now to specify the font of the text, let's say 0, or we can say, you can either put an index, or we can say cv2.font Hershey plain. We have a few fonts in Opencv that we can use. We don't really care now how the font looks like for this exercise, so just go with anything like this. And then the size of the text, let's say 1, and then the color of the text, let's use the same color, 0, 0, 225, and the thickness of the text, we say 2. And let's now run this one. So I want just to make sure that there are no typos, that the put text is correct, and there is some problem, of course. Cannot unpack numpy int 64 objects on line 19. Okay, so I'm extracting bounding box and classes, but then first is bounding box and then class. So I need to invert this. Bounding box, so now it should be correct. And we can see now there is a number, which is 16. So 16 is the class related to the dogs. So we have 16 for both of them. Of course, we have only 2 dogs, so we have the class of dogs. Now you might be wondering, how can we show the class for this? We can also show the class. I want to show you how the class is. So usually we have a text file that's associated with the index. So 16, so this is the text file where for each line we have a class name. This pre-trained model can detect 80 different classes from Coco dataset. And among these 80 different classes, we have like person, bicycle, car, motorbike, and so on. So they are very common objects. And then we have the dog, which is the 17th line. So it's, consider we start counting from 0, it's the class 16. So I will not do this in this video because it will take too long, and that's not the purpose of this video, but you can load the text file into an array and then you associate. So from this array, you put the index, load from this array of classes, index 16, which will be the dog. So that's how you will have the class name also. And that's pretty good. We are showing like the object that we are detecting, and we are also getting the class. So if you load, for example, a video where it shows a person, it will be class 0 because person is the first class. So I recommend for you to try this with different objects. I'm going to put like the class list anyway in the code that you can download from the blog post. So everything you will find in the blog post, so that you can play with all these 80 different objects that you will see right here for your own project. And that's so far for object detection in general. Let's now, for the code, let's now run this in real time, because that's the first thing, crucial point for me of this video, to see how fast is this on Mac M1 and can we make it faster. So let's first run this and see how this is performing now. So what we see right now is the video, which is going very, very slow because it's performing object detection with deep learning. So of course, the speed is going to decrease in comparison with just loading a video. Here below, we have some benchmarks for how fast this is processing. These benchmarks are referred to each single frame. So for example, we have, let's take this frame, it took around 487 milliseconds to be processed, so it means that it's taking half a second to process a single frame. This means that we have only an FPS frame per second of 2, which is really bad. Let's say it's very, very bad to 2 frames per second. But you need to know one thing. We are not leveraging yet the GPU from the Mac M1. So by default, it's using the CPU. It's not leveraging the Mac GPU. So what we need to do is we need to enable the MPS backend from PyTorch. First, let's make sure that the MPS backend is enabled. So we can test this by importing PyTorch. So import torch, and then we have torch. So it's print torch.backend.mps.is available. Let's now run this one. Before everything we can do, before we load the model. So this is going to tell us just true or false. Okay, true. That's all we need. So the MPS is available. By default, when you install Ultralytics, also the MPS for the Mac is installed. There is some requirements. First, of course, you need to have like the Mac M1 or and also you need to have like, there is some OS version. I'm not sure about which is like the minimum OS version from the Mac for this to work, but I will put that from, I will put like the official information from PyTorch, so there is no mistake on that. So we have the MPS available, but it's not enabled now for the detection. What we need to do is we need to tell the Ultralytics library that for the processing of this, we want to use the MPS device. So right here, when we're using the model to detect the frame, we need to add device and then equals, and then between quotation marks, so this is a text, we say MPS. So this is an option that we use we can use for different devices. So we can choose like CPU, or if we are using a computer, either Windows or Linux with Nvidia graphic cards, we can choose also what graphic card do we want to run in case we have multiple graphic cards. So let's now run this with the MPS. So if you remember on the benchmarks, before we were getting around 2 frames a second, so half seconds to process a frame. And you can see how incredible it's now, like the speed leveraging the Mac GPU. So now we're processing the video pretty much in real time. So I'll leave this go for a bit. So we have now object detection in real time on the Mac M1. If we check now the benchmarks, the speed is more than 10 times faster. We were processing around 490, 480 milliseconds for one image. Now for just one image, it is taking 42 milliseconds, which is incredible. I was very impressed by this result when I ran this object detection first on the Mac M1. I was so surprised because it's not so far from the good Nvidia RTX graphic cards for object detection. So this result is very, very impressive for such device. I'm testing this on Mac M1 Mini, so it's very, very impressive. And this is it. For object detection at Mac M1, you need to run this basic code. You put device MPS to leverage the Mac M1 device, and then the object detection will run on this. This code will be available for downloading below. Again, I recommend you do this by yourself for this exercise. it can be improved a lot. For example, we can add the classes, we can add different colors for like different classes. We can improve like the structure of the code by creating some functions, putting the functions in another file so that the main code is very clean. So that's what we should do for a project, but for this, it's a great start for you to learn object detection and play around with the Mac M1 or even other devices, because like the process is very similar on Windows and Linux. And now let's do some benchmarks. So Mac M1, around 500 milliseconds, let's say, for the CPU, around 40 milliseconds for the GPU. Let's now see how this is working on Windows with the Nvidia RTX 3060. So I'm now testing the exact same code on Windows. In this computer I have two graphic cards, an Nvidia RTX 3060, which we see right here, and then I have an Nvidia GTX 1660 Ti. So I'm going to start first with the RTX 3060. So instead of MPS, I'm going to use device 0, which is the first GPU. So remember, MPS for the Mac to leverage the Mac GPU, CPU to just load from the CPU, and then when we have Nvidia devices, we put 0 for the first, 1 for the second, and so on. Also, I will not get into details of the installation, but the installation for PyTorch on Windows and Linux for the Nvidia GPU needs to have another step, which we need to install PyTorch with CUDA and so on, in case it's not working if you do the same test. Device 0, so I'm going now to run this one, so let's run. So it's same code, same exact video, so you see Python 3.9, CUDA, Nvidia RTX 3060, and this is the benchmark. So we have around 16 milliseconds per image. I can say that the image, like the GPU, it's not fully used because the code can be optimized. But at the same time, so we see that the GPU is used around 50% of its capability. But still, at the same time, we have a performance, of course, faster than the Mac M1, but not so much faster, so not so impressive in comparison with the Mac M1. So we had like around 40 milliseconds for Mac M1 GPU. Here we're around 80 milliseconds. Again, I can say here it can be, of course, even improved. So if we average the GPU more than this, we can even like drop in half like the timing, so we can double up the speed. Let's also test with another older GPU, the Nvidia GTX 1660 Ti. So let's run with device 1 and let's see what we get. Device 1, GTX 1660 Ti with 6 GB of video RAM, and we get around 23-40 milliseconds. So this is closer to the Mac. No, it's still faster, of course, but we're talking about good, both of them good Nvidia graphic cards, still faster, but not so much faster. We have around 23 to 30 milliseconds per image. Let's do a last testing with CPU. I have a AMD Ryzen 5, should be AMD Ryzen 5 2600. It's a bit old of a CPU for this, and we get similar performance to the Mac, around half second per image. I hope that this video was useful for you to play around with object detection on your Mac. If you want to know more about object detection and building projects, you can check the courses that I have at pysource.com. If you have a company or a startup and you want me to build your project, you can contact me from pysource.com. There is a contact form where you can ask for a quote for your project. This is all for this video. See you in the next one.